Welcome to Getting Started with Application Acceleration Manager's Symmetric Optimization. Symmetric optimization helps businesses efficiently move large quantities of data across a wide area network. In this training, we give a high overview of Application Acceleration Manager's Symmetric Optimization feature, then examine more detailed features of the symmetric optimization environment, such as symmetric data deduplication, compression, and I-session connections, among other things. We configure symmetric optimization at a high level and share additional resources. An overview of symmetric optimization. BIG-IP Application Acceleration Manager, or AAM, increases server capacity through compression offload and sophisticated caching. It does this by providing web acceleration and wide area network, or WAN, optimization features that help reduce network traffic flow. AAM contains many functionalities, which can loosely be divided into three categories: web acceleration, symmetric optimization, and managing traffic with bandwidth controller and rate shaping. In F5 University, we provide training on web acceleration and symmetric optimization. For this training, we look only at symmetric optimization. Web acceleration can improve web application performance by providing acceleration functions like content caching and image optimization. The symmetric optimization feature is useful to organizations that need to move lots of data over a WAN between two or more points they control, such as between two data centers. It works great for backups, synchronization, and collaboration for applications, databases, and file management systems. Note, additional search terms for AAM are WAM and WOM. This is because symmetric optimization was formerly known as WOM, or WAN Optimization Manager. This is not to be confused with symmetric mode found in the web acceleration function. The web acceleration function was formerly the product Web Accelerator, which was then folded into the Web Acceleration Manager, or WAM. Now both WOM and WAM functionalities reside in one product, AAM. AAM is not supported on F5's iSeries hardware. Most businesses experience a WAN that does not respond as quickly or as precisely as a LAN, resulting in slow application or services response time. To speed up network functions, enterprises need the WAN to perform more like a LAN. Symmetric optimization is a way to make the WAN feel more like a LAN. It optimizes packet flow between BIG-IPs across the WAN. It requires a BIG-IP on each side of the WAN to perform these optimization functions. It leverages I-sessions, F5's secure communications method, for reducing the volume of data being sent across the WAN, and it requires an AAM license. Symmetric optimization does not fix network problems. Rather, it eliminates the symptoms of latency or dramatically improves them. Thus, it optimizes the flow on both sides of the WAN. It does this by using compression techniques, deflating techniques, and symmetric data deduplication. It also optimizes data flow by reusing connections. Symmetric optimization is built on a chain of services that processes traffic before it's sent across a WAN. For example, compression can apply the codecs LZO, deflate compression, or bzip2. With TCP optimization, you can leverage F5's highly optimized TCP IP stacks. With symmetric data deduplication, resending duplicate data is eliminated. Traffic to be optimized goes through 6 services. Traffic optimization techniques may be applied at each step based on configuration settings. The more services utilized, typically the better optimized the traffic is coming out the chain of services. With less data being sent across the WAN, transit times are reduced, resulting in a better experience for users. Symmetric optimization services. The first optimization feature we discuss is application optimization. We can optimize many applications by dramatically accelerating application layer performance. The application performance features of AAM reduce or delay client-server transactions and overall protocol chattiness, improve network protocol behavior and thus increase available bandwidth, and allow application protocols to communicate more efficiently. Some of the optimized applications that are available as templates in BIG-IP are listed on this screen. For the purposes of this training, we use the example of CIFS optimization. Without application optimization, each query moves all the way across the WAN and is acknowledged by a response that must also traverse the entire WAN. Since CIFS is a chatty protocol, communication happens frequently, which can add to network congestion. In this simplified diagram, the vertical lines represent time. The further down the line, the longer the interaction takes. Without symmetric optimization, each response comes later than the previous response, adding latency to network functioning. The TCP three-way handshake can be optimized by enabling TCP Fast Open, or TFO, on the BIG-IP. This speeds up the opening of successive TCP connections by sending the initial SYN packet along with the TFO cookie to authenticate itself. This allows for the request to be sent before the final ACK is received in the three-way handshake. Then, with application optimization, the BIG-IP continues to make subsequent requests and acknowledgments a lot more efficient by replying to some communication locally without having to wait for a response from the server on the other side of the WAN. The BIG-IP can gather and respond to many such requests. This is called pipelining and results in more efficient communication and faster delivery of requested data. The time of the last response is a visual representation of how latency has been reduced. Symmetric data deduplication is an acceleration technique that is enabled by default in AAM. It involves storing byte patterns and replacing them with a hash index. As byte patterns traverse the WAN, the byte patterns are noted and referenced with a hash index. They are then cataloged into a dictionary by both BIG-IPs. The dictionary is stored on the data store, which is maintained between both systems. The second time the same byte pattern is seen, the BIG-IP replaces the pattern with the index, then sends it through. When exiting the WAN, the BIG-IP on the other side of the WAN sees the index. It then sends the original byte pattern in its place. This optimization method is protocol independent and data format independent. What this means is that the byte pattern can appear in one protocol, like TCP, and then another like HTTP, and it will still be deduplicated correctly. Likewise, if the first transfer is a download like an email attachment and the second one is an upload like a Windows file share, the byte pattern is still recorded and still rendered flawlessly on the other side of the WAN. Additionally, when the BIG-IP obtains a packet, it can compress it before sending it away from the TCP stack. The packet is then decompressed on the other side of the WAN. This is a session layer compression and can be configured with the following codecs: deflate compression, which is a combination of LZO and Huffman algorithms; LZO alone, which offers good compression at a reasonable workload for the CPU and is more CPU friendly than the deflate codec; and bzip2 codec, which is suited to lower speeds. F5's adaptive compression setting is not a codec, but is the most flexible compression setting because it decides whether or not to compress based on CPU usage and traffic. What this means is that adaptive compression weighs the possible added latency of compressing and decompressing traffic against the amount of current network congestion. It then selects the appropriate codec based on that determination. Next, SSL encryption provides certificate-based authentication of optimized traffic, ensuring that the transfer of data through iSessions is secure. TCP optimization is not unique to symmetric optimization, but is a main feature of F5's Traffic Management Operating System, or TMOS. F5's highly optimized TCP IP stack impacts delivery in a WAN setting by applying session-level application awareness and persistent connections, thus maximizing throughput and performance. And lastly, bandwidth allocation managed by the rate shaping feature of AAM is an optimization feature that's available on BIG-IP. With quality of service rate shaping, the bandwidth consumed can be downsized for less important network activities, and at the same time, important and critical data transfers can be prioritized. This optimizes bandwidth to prioritize the transfer of the data that's most important to the enterprise. In this example, several applications consumed a greater amount of bandwidth than vMotion. Using TCP optimization, more bandwidth was allocated to vMotion when crossing the WAN, and available bandwidth was reduced for other applications. In this way, transaction integrity was optimized for the virtual machines running this particular application. iSession is the mechanism that enables symmetric deduplication and compression. You already know that big IP AAM systems communicate in pairs on opposite sides of the WAN for symmetric optimization to function. But after optimization, compression, and/or data deduplication on one big IP, that traffic must flow across the WAN through an iSession connection to the big IP on the other side. To make this work, each big IP AAM system includes an iSession endpoint, resulting in a simple point-to-point configuration. You can think of an iSession endpoint as the function that optimizes and wraps the data for transmission over an iSession connection which utilizes TCP. The iSession connections themselves consist of two parts, a control channel and a data channel. The control channel is established independently of the data channel. It's what allows the big IP systems on either side of the WAN to exchange parameters and advertised routes and show the other endpoint as available. No user traffic flows over the control channel. The data channel is the optimized user traffic that flows through an iSession connection. Configuring symmetric optimization. Loosely, in order to configure symmetric optimization, you first need to check that traffic can flow unimpeded between your two big IPs. This involves creating a few configuration objects. Then you can use the Quick Start template to configure the actual optimization objects. Clients on what we are going to call the local side of the WAN request data from servers on the other side of the WAN, the side we're going to call the remote side. Client requests leave the local LAN, move through routers, and are acknowledged by servers on the remote LAN. With the introduction of big IPs, which are default deny devices, traffic is halted and must be enabled. Since a big IP on each side of the WAN is necessary for symmetric optimization, we must first get traffic flowing between them before we begin configuring symmetric optimization. First, we create a listening virtual server on the big IP sitting in the local LAN. This will be a wildcard virtual server that we configure to simply forward traffic across the WAN. The big IP on the other side, the remote LAN, also needs a forwarding virtual server so that it can listen for traffic coming across the WAN and forward the requests to the appropriate backend servers. Next, both big IPs need WAN self-IPs, so one must be created for each side. Setting port lockdown to allow none permits symmetric optimization to control these self-IPs and use them for optimized traffic only. The last objects needed to enable traffic flow are advertised routes. An advertised route is a subnet that can be reached through the local big IP and needs to be sent to the other big IP in order to be used. After the symmetric optimization big IPs in pairs have been configured and connected, they automatically exchange advertised routes between themselves. Once these subnets are exchanged, then traffic destined across the WAN can be optimized, such as in this example, where traffic is initiated on the local side and routed to the remote servers in network B. Now the big IPs contain all objects necessary to check for traffic flow. All that remains is for you to ensure that your client requests on the local side are reaching the designated server on the remote side. This can be done with a TCP-based networking utility such as Netcat. To ensure traffic flow, you've created some optimization objects and checked traffic. Now you can run the Quick Start template to finish configuring your symmetric optimization environment. Running the Quick Start template creates additional configuration objects. It creates endpoints or virtual servers that contain the iSession profile and control iSession connections. And it creates the application virtual servers that vary according to which type of application traffic you want optimized. Let's see what this process looks like in the configuration utility. Though not a part of the Quick Start template, remember that port lockdowns are generally set to allow none to avoid potential conflicts with other TCP applications. Advanced users can select Allow Custom if they choose to open ports for other required services. Now we launch the Quick Start template itself for the remaining configuration items. From the Acceleration tab Quick Start, we run a Symmetric Properties configuration template by filling in the pertinent fields. This must be done on both sides of the WAN. In the Quick Start template, we fill in these fields. The local endpoint, here we set the WAN self-IP address of the local endpoint. This will be where the iSession tunnel starts and ends on this particular big IP system. The VLAN of the LAN side and the VLAN of the tunnel or WAN side. Scrolling down, we designate our outbound and inbound iSession authentication profiles as SSL and click Apply. Within the Acceleration tab, but on the Symmetric Optimization flyout, we view the Listeners tab. You can see that Quick Start created an iSession virtual server. This is also a listener, but in this case it's listening for iSession traffic. From the Properties tab, you can see the local endpoint objects that were created on the previous step. What's next is to repeat the procedure for the remote side Big IP. Launch the Quick Start template and select Symmetric Properties. Fill in all necessary fields such as self-IP and VLAN. And lastly, view that a virtual server and local endpoint for the remote LAN was created. Now that the endpoints for both sides are built, they detect each other using probes. As you can see when accessing Discovery from the Remote Endpoints flyout, the probes are specially designed ICMP and TCP requests that are SYN request packets sent from the Big IP. Running the probes renders a list of remote endpoints which then become available on the Remote Endpoints List tab. Note, IP addresses of remote endpoints can be entered manually. Now we move from the Remote Endpoints List tab to the Advertised Routes flyout. Here we set the actual route for symmetric optimization by telling each iSession virtual server what routes are available to that particular side. We click Create to configure a route and walk through the template. Here we see a route created to the 172.16 network. Moving to the iSession server on our local side, we see that it shows the route created by our remote symmetric optimization server. In one location, iApps create the necessary virtual servers and associated profiles to optimize the application traffic that you select. iApps are of particular use for symmetric optimization because a variety of listeners are needed to listen for specific protocols such as HTTP or FTP. The listeners then hand off that traffic to the iSession virtual server. From the iApps menu, click Application Services and Create to start this process. Your local environment will vary, but here we're only listening for CIFS traffic and only from the local LAN. From there, in the iApps configuration template, other fields are available for configuration, such as Network to set the network types, VLANs to choose which VLANs listen to client traffic, virtual servers specifying the listener by designating the location of the server, optimization, whether to encrypt, compress, or utilize symmetric data deduplication. You can learn more about AAM symmetric optimization techniques on F5 University, where you can view the free Getting Started with AAM Web Acceleration, the second half of the AAM story. Professional Services is another resource. They can assist you with your AAM needs, such as designing, customizing, or implementing the solution. Thank you for attending this F5 University training.